I hope you all enjoyed your lunch break and feel refreshed. We're getting started with our afternoon workshop now, and it's my pleasure to introduce our first speaker of the session, Nicolas Heess. Nicolas Heess is a research scientist at Google DeepMind. He is interested in questions related to artificial intelligence and machine learning, including perception, motor control, and robotics. One of his long-term goals is to develop embodied agents that learn to intelligently reason about and interact with their physical environment. He will be sharing his insight on simulation-based learning for real-world embodied intelligence. Please join me in giving him a warm welcome.
Well, thank you very much for the introduction. Thanks for having me. Thanks for organizing such a great and timely workshop. And thanks for making an effort to come back after lunch. I really appreciate it. I was a bit worried like 15 minutes ago. Anyway. So just to give you a flavor of what motivates my research, the slide shows several examples of everyday behavior that humans perform more or less effortlessly. And you wouldn't naturally consider these as examples of grand challenges for AI. But if you start thinking about what each of them entails, you may change your opinion. So all of them require rather sophisticated control of the body. They require you to perceive and understand the environment. They require you to understand and reason about goals at different temporal horizons. And you need to predict what others are going to do. And importantly, they require you to do so reliably across a broad variety of different conditions. So much of what's driven my research in the last 10 years or so is to understand the underlying computational principles and how we can recreate some of these abilities in artificial systems, both in simulation and in the real world. We all know that robot learning is hard for a number of reasons. And I'd say until just a few years ago, the path towards generally competent robots was rather unclear, at least to me. Now, but many things have changed, and intelligent robots now seem much more within reach than they used to be. And there are a few reasons, in my opinion. Firstly, we have figured out how we can use RL in large-scale simulation to synthesize complex behaviors and transfer them to the real world. We're also beginning to understand how simulation can be augmented with learning, thus improving scalability and realism. Secondly, we're getting better at making effective use of robot data. That includes algorithmic improvements to learn reliably via notation or RL, but also model architectures that allow us to generalize across tasks and embodiments, and that reduce the marginal cost of task acquisition, thus making the scarcity of robot data a lot less daunting. And lastly, we have started to understand how we can leverage other web-scale data, like text or images, to imbue robots with the general-purpose world knowledge that they require, but are unlikely to acquire otherwise, for instance, language and semantics. Now, I'm very excited about each of these three areas, but I know we'll hear more about points 2 and 3 in other talks in the workshop and other sessions of this conference. So what I want to focus on in this talk is the first point. More specifically, I want to talk about how to synthesize complex behaviors with RL, how to transfer behaviors to real robots, and how to improve simulation with learning. So the work that I'm presenting today in some way started with the results shown on this slide. In this study, we had put several different walkers into diverse parkour-like environments. The environments contained obstacles of many different shapes and difficulty levels, but the reward was simple, basically just incentivizing forward velocity and not falling. And to our great surprise, the agents ended up learning rather sophisticated movement strategies. And the fact that RL, when exposed to enough diversity in the curriculum, can lead to the emergence of complex behaviors may seem trivial now, but it felt like a bit of a game changer at the time. And in subsequent years, we have been looking at augmenting this basic idea with other techniques, some of which I want to give a few examples of now. So for instance, we've investigated how we can avoid engineering the diversity and have it self-generated by the learning system through training in a multi-agent setting. And we also want to know whether the pressure of agents competing with each other can lead to the emergence of high-level cooperative strategies. Indeed, the agents in the video here were trained by playing games against each other with a simple reward just for scoring. But as you can see, they've discovered much more than just rushing towards the goal. They move into the spaces, pay attention to their teammates, and play passes. Another important line of investigation has been that into reusable skills. Many complex tasks, especially with high-dimensional bodies such as humanoids, are difficult to learn from scratch. To mitigate this issue, we've studied learning of skill representations that can be reused across different scenarios. And in particular, we have studied how we can derive naturalistic and functional movements, for instance, from human motion capture data, and how we can subsequently combine these skills via RL to solve complex tasks. In the example on this slide, we've derived movement skills for coarse object manipulation from human motion capture data. And we then use these skills to learn controllers for relatively complex object manipulation tasks using egocentric perception. And we've also investigated how these ideas can be transferred to real robots. In this example, we have derived natural movement skills for quadruped robots from dog motion capture data. And the skills make it easier to learn complex tasks in simulation, and importantly, they can be transferred safely to the real robot. The video shows a controller based on dog movement skills that can directly imitate dog movements zero shot in the real world. And finally, we've looked at how we can augment simulation with learned components. Creating realistic simulation of diverse scenarios comes at a significant cost. In this work, we've created nerves of real-world scenes and combined them with Mujoko. We used the nerve-derived mesh of the environment to provide the collision geometry and the nerve's rendering function as a neural camera. And we then trained agents in these hybrid environments with RGB vision and transferred them to the real world, zero shot with good success. So in the rest of the talk, I want to show two recent examples in which we combine the ideas from the previous slides in two advanced scenarios. Both are motivated by human soccer, which is a multifaceted challenge for motor control and higher level intelligence. The first study focuses on how we can synthesize complex behaviors in simulation. And the second study then brings these ideas to real robots, combining behavior synthesis with sim to real and real to sim. Human football or soccer is a great testbed for many aspects of embodied AI. It requires a combination of sophisticated motor control, long horizon planning, coordination, and competition. The first example of my talk was designed to test whether we can scale reinforcement learning to a considerably more complex scenario than had previously been considered for motor control, both in terms of the embodiment and in terms of the task complexity. So for this study, we created a simplified artificial soccer environment. With realistically simulated physics, the players are humanoid characters with 56 degrees of freedom, which are rewarded for scoring a goal. The environment didn't have the full complexity of real human soccer. For instance, there are no fouls and the ball cannot leave the pitch. And for most of our experiments, we instantiated with only 2 players, mostly for competition. Although we consider a simplified version of soccer, the task remains pretty challenging. In particular, the agent needs to learn behavior at different levels of abstraction. It needs to learn about robust and dynamic low-level motor control. It needs to learn mid-level goal-directed behavior, such as dribbling and shooting. And it needs to learn high-level planning, such as positioning on the pitch, coordinating with teammates, and paying attention to opponents. Importantly, these different levels of control can't be treated in separation, but have to be closely integrated. Our solution is loosely inspired by human learning, and we train our agents in a gradual fashion. We first teach them low-level movement skills. We then teach them mid-level soccer skills like running, turning, dribbling, kicking, and so on. And we finally teach them goal-directed and coordinated soccer gameplay. To this end, we use multiple different learning signals: imitation learning for low-level movement skills, reinforcement learning with well-defined rewards for the mid-level skills, and finally, multi-agent RL and self-play for discovery of cooperative strategies. To obtain general-purpose low-level movement skills, we used motion capture data from human freeform soccer. We trained a policy to track a diverse set of motion capture reference clips. The policy consisted of 2 components. The first is an encoder that translates future poses into latent embedding or motor command. And the second is a decoder or low-level controller that translates the desired future pose encoded in this motor command and the current pose of the body into actions that are likely to achieve that desired pose. The full system can be seen as a general purpose imitation policy that can reproduce arbitrary motion capture trajectories. And this is actually what you saw on the earlier slide with the quadruped robot imitating a dog. And more importantly, though, the low-level controller or decoder can subsequently be used as a general-purpose motor module that can be controlled by the embedding space or motor command, for instance, as part of a policy that then solves specific tasks. Now, to learn soccer, the skill module itself was not sufficient. It induces naturalistic low-level movements, but it does not directly incentivize or induce goal-directed behavior like interacting with the ball. So to achieve this, we created a set of mid-level skills. We set up a number of training drills that seemed relevant for soccer and trained policies to solve them via RL. The policies for these drills used the previously trained low-level controller and were thus constrained to approximately human-like movements. We trained 4 different drills following a target, so running and turning rapidly, dribbling, kicking, and shooting at the goal. The video here shows one example, a dribble expert that was trained to dribble the ball following a target. After training, the drill experts were dependent on drill-specific information like the target to follow during dribbling. To turn these experts into general-purpose skills, we distilled the expert policies into mid-level skill priors via distillation with information asymmetry. This is illustrated on the right here. For instance, to learn a general-purpose dribble skill or prior, we executed the expert while it was following a target, and we then copied its behavior into the drill prior, but did not give the drill prior access to the target position. The consequence is a policy that effectively represents dribbling towards arbitrary goals. When executed, it dribbles in different directions, turning seemingly randomly every so often. Now, with the low-level skill module and the mid-level skill priors in place, we were ready to train the full soccer players. We train them by playing 2 versus 2 football matches, making use of the previously learned skills. And to facilitate learning, we make sure that the players produce to facilitate learning and to make sure that the players produce sensible movements, they make use of the pre-trained low-level skill module. That means instead of taking actions directly, the agent produces motor commands that are translated by the low-level skill module into actual actions. And this effectively constrains the behavior of the agents to the space of human-like movements. We use the mid-level skills to bias the players towards behavior relevant for soccer, such as interaction with the ball. And to this end, we regularize the players towards the mid-level skills learned in the previous step. Regularization here means that we introduce an additional term in the cost function in addition to the task reward, which basically encourages the agent's behavior to be similar to the mid-level skills represented by the priors without imposing a hard constraint on the final solution. And the fact that the players can deviate from the pre-trained mid-level skills is really important here. Soccer behavior is obviously very context dependent, and the space of behavioral strategies is vast. So and it's certainly much richer than the 4 drill priors that we obtained during the pre-training. The regularization approach allows the agents to be influenced by the drill priors early in learning, but to then deviate from them as learning progresses. Finally, the high-level strategies are hard to handcraft or specify via reward, and to obtain high-performing soccer players, we rely on multi-agent RL and train the players with population-based self-play. That means we have a population of 16 different players which play matches against each other, and for each game we play 2 pairs of identical players against each other. As explained on the previous slide, the agents make use of the low-level controller and are regularized against the mid-level skills or drill priors. The advantage of population-based self-play is twofold. Firstly, the agents play against each other and improve together. This leads to a natural curriculum. It means the task is basically never too easy or never too hard. They can learn well. And as shown in the previous work, this type of auto-curriculum can lead to the discovery of very complex strategies. And secondly, the fact that we have a population of players means that each agent has to learn to cope with different opponents, which leads to additional robustness of what they're learning. Now, here's some highlights from the resulting gameplay. The video, I think, is pretty self-explanatory, but a few things are worth noting. So firstly, the agility of the players, the movement capabilities and the robustness go well beyond what was achieved, for instance, during training of the mid-level skills. They're very capable of handling the ball, much more competently, again, than what they had learned in the skill training phase. And they've also learned to pay attention to their teammates and opponents. So for instance, they take turns. If one player is close to the ball, the other moves forward to receive a pass, or they position themselves defensively as a function of the ball in the other player. Just going to let this play for a few seconds. pretty good in simulation, maybe not what you would want to put on your robot. Turn taking here. It's really the interplay of the different skills and the multi-agent training that leads to these relatively sophisticated behaviors. Now, creating complex behaviors in simulation can teach us about the computational principles of how to get there and embodied AI, but ultimately we want to bring these capabilities of the real world. Maybe these weren't quite there yet. So in the second part of the talk, I want to discuss how we've applied the insights of this previous study to soccer with real robots. So for this, we consider a setup that bears some similarity to the one used in the simulation study. The pitch is enclosed by foam ramps to prevent the ball from leaving the pitch. And to simplify things, we use a motion capture system to estimate the robots in the ball's position. The robot that we use is a small hobby-grade humanoid, the OP3, with 20 degrees of freedom. For training, we adopted a sim-to-real approach. That means we trained the policy in simulation and then transferred it to the robot zero shot. For training and simulation, we roughly matched the real environment and rewarded the agents for scoring. And the setup posed two major challenges. Firstly, creating safe and performant policies in simulation. And secondly, transferring this behavior to the real robot. And the sim-to-real gap here was particularly pronounced in this case because of the low-cost nature of the robot, which means less precise sensors, less joints with more play, and overall less robust hardware. Training in simulation posed similar challenges to training of the humanoids in the previous study. In particular, when attempting to train end-to-end from scratch, the agents either learn nonsensical behavior, like what's shown here, or they wouldn't learn at all. Or not safe on the robot. And furthermore, we also furthermore, we also needed to ensure that the behaviors would be safe to be executed on the real robots. And this required us to be able to impose certain constraints on the solution. We therefore adopted an approach similar to the one for the humanoids. We divided training into two phases. We first trained multiple skills separately in phase one. We then composed them to achieve full gameplay in phase two. So in this setting, we found that the simple decomposition into just two skills was already effective, a get-up skill and a soccer skill that consisted of walking and kicking. Unlike for the humanoids, we also didn't use any motion capture. So for the get-up skill, we used a scripted trajectory as a reference to ensure that the behavior would be robust, but also safe to execute on the robot. We find that scripted trajectory via RL. And then the walking and kicking skill was simply trained end-to-end from real robots. In the second stage, we used multi-agent RL with self-play to train the players, relying on the previously learned skills to facilitate learning. This is very similar to the way we trained the humanoids in the final stage of the previous study. We used self-play to benefit from the auto-curriculum and used the skills via regularization. There were some simplifications compared to the humanoid study. Firstly, we did not maintain a full population, but simply played the agent against old copies of itself. And secondly, since we only had two skills, we were able to explicitly switch the regularization between the skills depending on the game state. We also adjusted the regularization strength automatically as a function of agent's performance. So the video here shows some snippets of gameplays during training and simulations. Get the point. So the plot here on the left actually shows that the impact of self-play and regularization towards the two skills. So without regularization towards the skills and without self-play and the resulting auto-curriculum, the performance was markedly worse. So transferring behavior from simulation to the real world posed several challenges. To mitigate the differences between simulation and the real robot, we combined several ideas. Firstly, we matched the simulation to the real world as closely as possible, identifying, for instance, the parameters of the actuator model. We also varied a small number of difficult to estimate simulation parameters like flow friction, IMU orientation. and a few other parameters. And then we also improved the robot's control stack to allow for higher control rates of 30 Hertz and thus effective feedback control, and also removing some of the observation latencies that wouldn't be present in simulation. And finally, we applied random perturbations to the robot during training as shown in this video. So these red squares here indicate perturbations. And all of this was important to get robust and transferable behaviors, including the modifications to the control stack. So, but even with a reasonable sim-to-real transfer, the lack of robustness of the hardware caused us some headache. Let's do this in the video here. In particular, we initially had a large number of breakages, so you can see that. And the robot behavior would change over time, for instance, because body parts would deform. It's really a relatively more hobby robot. Now, to mitigate some of these effects, we made some changes to the hardware, as shown on the left here. For instance, we added bumpers to dampen the robot's fall and modified the hands so that they wouldn't get stuck in other robot parts. And to mitigate other problems, we regularized the behaviors learned in simulation. So for instance, many of the actuator breakages that we encountered were caused by high torque transients in the knees. And you can see these transients here in the video. And to address this issue, we applied some regularization during training, effectively penalizing these spikes, which made a big difference to our ability to keep the robots alive for longer. Right, let me show you some results of all of this. So they were quite surprising, really, to us. So obviously, the robot behavior is still somewhat clumsy, but it's so much more agile than anything we'd ever expected from the OP3, and especially when you contrast this with the built-in behavior that's provided with the robot. I remember when Thomas first showed me running of the OP3 in simulation a few years ago when he advocated for the platform. I was kind of incredulous that this would be possible, but now he actually made it happen. So the robots, you can see how the robots transition smoothly between different skills. They adapt their movements to the game context. They show some real kicks and defensive moves. And they also learn to respond to their opponent in the ball and, for instance, position themselves cleverly on the pitch to block shots. Just going to let this play for a little while. It's quite fun to watch. And as several people have verified, this is actually not a demo effect here, but it is pretty reliable. Now, if you're not convinced that this behavior is relatively impressive, maybe this is the contrast to the built-in behavior, which is so much slower and so much less agile and less dynamic. So this is a slow motion video that shows walking, kicking, and getting up, and shows a side-by-side comparison of learned movement skills with the counterparts that are delivered with the robot. Yeah, and I think the agility and dynamicism of the learned skills is really particularly obvious in this setting. You can see how the learned policies exploit the hardware and push it to its limits. You can see how the robot leans forward, for instance, during running and propels itself forward with the toes, and it really leans into the kick here, as you can see. Another interesting analysis is that of the high-level strategies that were learned. So here we do this by looking at set pieces. In all four examples, the robot moves towards the ball and then kicks to score. On the left-hand side, we demonstrate the opponent awareness when the robot is in offensive play. When the path to the ball is clear, the agent approaches it straight. And if the opponent is standing in the way, then the robot walks around it, as you can see in the bottom. On the right-hand side, you see defensive behavior. Again, if the opponent is far away from the ball, the robot moves straight towards the ball. However, if the opponent is close to the ball and there's a danger of the other player scoring, then the agent approaches the ball in a way that also blocks the shot towards the goal, as you can see again in the bottom. Now, one major limitation of the results presented so far is that the players depend on an external state estimate for their position on the pitch and the position of the ball and the other player. Now, the OP3 robot does come with an RGB camera, but learning to play soccer relying only on this camera for perception is challenging since the environment is observed, dynamic. So we have some preliminary results for vision-based policies. These were obtained with a modified sim-to-real pipeline, similar to the one mentioned at the beginning, involving a real-to-sim step. So this is the standard sim-to-real pipeline. But to mitigate the visual sim-to-real gap, we estimate the nerve of the soccer pitch and use that to obtain a neural rendering function to simulate the player's camera. So the video shows visualization of the nerve here. And this video shows a snippet of training and simulation. The inset in the bottom left shows the agent's view that we obtain with the nerve rendering function in the place of the robot's camera. With this, we train an RGB-based policy end-to-end. Here are some preliminary results in the real robot. So the agent performs well in set pieces, such as penalty shoot. Bottom left, again, is the agent's view, a bit higher resolution than what the agent actually sees. And during normal gameplay, they show sensible behavior. They're able to kick and locate the ball. And they also show some search behavior. But they do sometimes lose track of the ball or their position on the pitch. And some of these issues are also present in simulation, which indicates actually the need for better training strategies for heavily partially observed settings, such as this one here. Now, that takes me to the end of the talk. I've shown a few examples how RL can be a powerful tool for synthesizing complex behaviors for embodied systems, behaviors that would be hard to handcraft, and how with the right tools, we can effectively combine low-level motor control with high-level strategies. I've also shown how such learned behaviors can really push the embodiment to its limits, even for real hardware. In our case, achieving much more dynamic movements than we ever expected to see for the OP3 robot. Obviously, there's still a number of unsolved challenges. On the learning side, there's, for instance, more work that needs to be done to develop strategy to reliably combine behavior with perception. And similarly, there are many open questions associated with the use of simulation to train real robots. They have to do with the fidelity of the simulator, but also the cost of creating rich simulations. Yeah. So despite for instance, in our case, we made quite a big effort to transfer from simulation to the real world, but it wasn't as good as we would have liked it to be. And also just the loop of mapping the real world onto the simulation was far too slow. But given recent progress in learning representations for 3D scenes and video models and generative AI, though, I'm somewhat optimistic that learning may help us to overcome some of these challenges, and that maybe the line between classical simulation and learned world models will eventually blur. I also think that perhaps recent results for training foundation models for embodied systems may eventually help us to blend learning and simulation and real data more effectively than is currently possible with a naive zero-shot sim-to-real scenario. Now, this takes me back to the 3 areas of innovation from the beginning of my talk. So simulation for robot learning is one area that has recently made substantial progress and led to some meaningful real-world deployments of robots. But I wouldn't want to argue that simulation and sim-to-real is in its current form are anywhere close to solving robotics. In my mind, the role that simulation will play relative to real data is still a bit unclear. My best expectation is that it will be one component in a mix with some of the other innovations that we'll hear more about sort of later today and in other talks throughout the conference. And if you're interested in reading more about those, I would encourage you to have a look at some of our recent papers, like to learn more about large-scale models of behavior that can generalize across tasks and embodiments. You can also quickly adapt. You can check out the RoboCat paper or the RTX paper. And RTX will also present during the keynote talk on Thursday. And for the latest results on how to combine behavior with general knowledge about the world derived from web data, you can have a look at the poster of RT2 on Wednesday. And with that, I'll stop and thank all the people who did the actual work and you for listening.
Thank you, Nicolas, for the engaging talk. Are there any questions in the audience? Yes.
Hi, thanks for the talk. I noticed that you select human mocap data for higher degrees of freedom simulation, but you select script standing motion for lower dimensional sim to real work. Can you give us more reasons for this different choice? And also, as for the mocap data, did you design the same data tab, degrees of freedom for mocap data and the simulation of robotics? Yeah.
So we only use the scripted. So for the OP3s, we only use the scripted behavior as a reference, basically, for the get-up movements. All the other behaviors were sort of learned just end-to-end with RL, and just standard rewards were sufficient there, basically. We did actually had a previous study. So in the study with the dog motion capture data, we also did map some of the human motion capture onto the OP3, and that was somewhat possible. Back then, the sim to real pipeline wasn't as good, so the results weren't as what we were hoping for. I think for soccer, it was just not needed in this case. So the robot just learned sufficiently well-constrained behaviors with the few tricks that I mentioned, basically. So it wasn't that we just didn't try it in this case. And it simplifies the pipeline.
So as for the mocap work, like, do you have the same degrees of freedom for simulation and mocap data?
I believe the way the motion capture data was retargeted with markers, we then tried to map those markers onto the humanoid body, but we didn't design the humanoid body specifically to match the motion capture data.
Great, thank you.
Yeah. And we've also mapped the same data onto lower degrees of freedom models, for instance.
Hi, thanks for the talk. I have actually two questions which are relevant to the multi-agent setting. So first of all, you were selecting 2 agents out of 16 to play against each other. Do the agents have different characteristics? And if they do, did you evaluate how these characteristics can affect the performance in those actions?
Yeah. So these are agents that at least nominally do have different characteristics, so different network parameters. So actually associated with each agent are different network parameters, but also different optimization parameters. And they get optimized in an sort of outer loop, basically. Over time, though, because of the way this is set up, the diversity in the population shrinks. And there are particular tricks that you can play to keep the population diverse, but we didn't do that specifically in the humanoid setting.
So they have different physical characteristics?
Well, sorry, it's not that the players have different physical characteristics. It's just that the network parameters are different. So we didn't make some players with shorter legs and other players with stronger actuators.
I see. And is there any communication between the teammates? No. Okay.
In this case, so they have to learn basically to know what the other player is going to do, to anticipate their behavior.
Gotcha. Thank you.
I will take one more question.
Thank you for the great presentation. I have a question about the soccer skills for both of them, both like the real robot and also the virtual ones. It seemed like you needed to add some additional help for it to learn. So like you need the motion capture data for one of them. Then you need to separate like the get up and the kicking skills separately, or else it did the funny behavior you showed. Do you think that'll always be the case for these complex tasks, that you need to inject this human help? And if so, what are the scalable ways to do that? And if not, well, how do you think we can overcome needing that?
Right. So I guess these days, whatever you say, something doesn't work. Like a few years later, someone shows you that it does actually work. So I wouldn't say that this will always be necessary. I mean, in the end, so I think in the end, they are actually, at least the OP3s are optimized end to end. And the influence, for instance, of these skills that we use at the beginning of training to regularize goes away over time. So I think they are to a large extent really to sort of steer the optimization towards the right local optimum. For the humanoids, the low-level controller at the moment is sort of fixed, but that provides in some ways weak constraints on the behavior, just sort of prevents the agent from doing crazy movements, basically. So it roughly constrains to the space of human-like movements. Whether we could take this away later in training, I suspect at the moment, no. Can we never take it away? Probably at some point we will figure out how to do it. But I think it's ultimately you can move many of these things also into reward terms, right? But then the optimization just becomes very difficult. And we found basically that sort of this particular way of I guess, in the end, sort of the regularization is a way of introducing extra rewards. It's more convenient than by creating like a very long list of shaping rewards, for instance.
Thank you.
And easier to optimize as well.
Great questions. Let's thank Nicolas again for the great talk.